Andrey Pilipenko on properties of random walk with membrane in multidimensional space. Please, Andrey.
Okay, today I will, so my talk is a joint work with Ilya Pavlukevich. Today I will consider the following model. I consider a random walk on z to the power m. For simplicity, I will consider only m equals 2 because it will be easier to make pictures. And I assume that transition probabilities are 1/4 to the left, to the right. So we make unit jumps with equal probabilities in each direction, everywhere except of hyperplane, except of y-axis. And I will call this y-axis a membrane. So here we have just simple random walk. And when you hit a membrane, then then transition probabilities are not 1/4 to the right, to the left, up or down. We assume that from this membrane, you can jump the neighboring layer.
Okay.
This is 1, this is -1.
Ich zeichne gar nichts.
But you can, the jump can be arbitrary. So you can jump to this point, to this point, to this.
Junge, ich bin so traurig, dass die Uni nicht verkauft.
With some probabilities.
50.000 neue Termine. Einfach im Impfzentrum.
I will assume also that this membrane have some periodical structure. What does it mean? I assume that there is some number, say d, period, such that transition from this point and from this point plus, okay, this distance is d, are similar. So let me write the rigorous definition. So I will assume that probability that x n plus 1 equals x1 y n plus 1 equals y1 given x n is 0, so you are here, and y n is y0 equals probability that x n plus 1 is x1 and y n plus 1 equals y1 plus d. Given x n is 0 and y n is y0 plus d. So probability from this point to jump here is the same as probability from this point to jump here. Probability from this point to jump to this point equals probability from this point to jump here, and so on and so forth. And the main question is as follows. Let's consider Donskoy's scaling. Let's consider this process. We scale time n times and space square root of n times. And the main question is to find a limit of this sequence. If there is no membrane, so if probabilities from this line are 1/4 to the right, to the left, up and down, then the limit is Brownian motion, two-dimensional Brownian motion. Today we will see that a limit now will not be a Brownian motion, but a Brownian motion with some membrane, semi-permeable membrane on y-axis.
Okay, and let me ask you about the first coordinate. It also has different limit, just x. One.
For x?
Yes, yes.
So a limit for x will be Excuberonian motion, and so the general result is as follows.
Okay, I see.
If we multiply this process by square root of m, where m is dimension, then the limit will be Excuberonian motion. So let me write Excuberonian motion. Skew for first coordinate, and some Brownian, independent Brownian motion by of t plus some constant times a local time of the first coordinate at 0 at the instant t.
Oh, now I understand. Maybe this is a Excuberonian motion just because the distribution of jumps from the vertical axis is not symmetric. Yes. If it will be symmetric, then we will have usual.
If it is symmetric, then we have usual Brownian motion.
Okay.
If not, then you have a Excuberonian motion, and you see the second coordinate is a Brownian motion plus a local time of the first coordinate at 0. So we may say that in some sense you have a Brownian motion here with semi-permeable membrane that pushes at some direction from this membrane. I will write a stochastic differential equation a little bit. Okay, a little bit later. Now I will consider what is Excuberonian motion, results about one case, and after this I will start to prove the result. For example, this membrane may be as follows. Some points may be like holes, like probability 1/2 to go to the right or to the left, or there may be some points that pushes you to the left with probability 1 or to the right with probability 1. For example, if you, so it is like one-sided door, like in a metro station. You may go only one direction, but you cannot go other direction. So when you come here, you may only exit or enter to the left half space. And now let me recall you what the definition of Ascubronian motion and some results about one-dimensional walks with perturbation. So there are few definitions of Ascubronian motion. The first definition is via Eta Excursion Theory. Let us draw a graph of reflected Brownian motion. So this is absolute value of a one-dimensional linear process. You have excursions. Okay, so excursion interval is interval between two zeros. So the process is not zero at this interval, and the process equals zero here and there. And then enumerate all excursions in some measurable way, and then toss a coin upon each excursion, and with probability P, leave it as it is, and with probability Q, flip a picture. For example, with probability Q, you flip this excursion, or for example, here you leave it as it is, here you leave it as it is, as it was, and here with you make this graph, and then the result is okay, this such process. So excursions with probabilities P are above zero, and with probability Q are below zero. Well, it is not simple to make a picture of a trajectory of a Brownian motion, because when you hit zero, then in any neighborhood of this point, there are infinite number of excursion to the right. So actually there is excursion here. So there are a lot of excursions here. So there is not so-called next excursion. So when excursion ends, there are infinite number of excursion in neighborhoods, in a neighborhood of this point. So this is a first definition of Ascubronian motion. The second definition is as follows. A process X is Ascubronian motion with a parameter gamma, gamma between -1 and 1, if this process is a solution to the following stochastic differential equation. dw of t plus gamma times local time of this process at zero at the time instant t. It was proved by Harrison and Shep that this stochastic differential equation has a unique strong solution if absolute value of gamma is less than or equal to 1, and there is no solution if absolute value of gamma is greater than 1. And the third way to give an equivalent definition of a Ascubronian motion is as follows. Ascubronian motion is a continuous Markov process with probability transition density function ptxy that equals phi of t x minus y plus gamma times sine of y times phi of t, absolute value of x plus absolute value of y, where phi of tx is a density of the normal distribution with zero mean and variance t. Probably it's better to write here dot instead of x. Well, and in this construction, gamma equals p minus q. I will also give Martingale representation for Ascubronian motion, but a little bit later. And now let me give you a link between a limit theorems, between some limit theorems for random walks and Ascubronian motion. The first result is probably due Harrison and Shep.
I'm sorry, may I ask a stupid
Yes.
question?
Mm-hmm.
So you have three definitions. In first definition, you have P and Q as parameters, and the
Yes.
second and third definitions, you have gamma. Ah, okay, I see.
Gamma is P minus Q.
Yeah, thank you. I have not noticed. Thank you.
And actually, if P is 1, then you have just reflected Brownian motion. If P is 0, then you have just a Brownian motion. Well, if P is 0, then gamma is 0, and skew-Brownian motion is just, and differential of skew-Brownian motion is just dW of t. And Harrison and Shep, they considered random walk xn on Z.
So once again, P and Q are not, the sum does not need to be 1.
Yeah,
P
Q is 1 minus P. Yes, P plus Q is 1.
Okay, yes, okay.
So with probability P, you leave it upwards, and with probability Q equals 1 minus P, you flip this excursion down. And the result is a skew-Brownian motion. If P equals Q equals 1/2, then each excursion is up with probability 1/2 and is down with probability 1/2. And it's clear that the result is just a linear process. Well, and now link between random walks and a skew-Brownian motion. Harrison and Shep considered the following random walk. It jumps, so jumps are 1 or -1, and probabilities to jump up or down are 1/2 everywhere except of 0, and probability to jump up from 0 is P, and probability to jump down is Q. And then here you have just usual random walk, 1/2 up and down, but when you hit 0, you go up or down with probability P and Q respectively. And they considered Donskir's scaling and studied the question, what is the limit? And they proved that the limit is a skew-Brownian motion with parameter gamma equals P minus Q. And you see the link here and here, when you may say here that you flip, you may start from reflecting random walk and then just flip excursions up or down, and it is not miracle that result will be like this. They calculated finite dimensional distributions and proved relative compactness, and the proof was straightforward. Another generalization is the following. Assume that you have a random walk integer valued random walk everywhere except of set minus mm. For example, +1 or -1 with probabilities 1/2. And here, transition probabilities are arbitrary. And you consider Donsker scaling and try to find the limit. And if all states of the random walk are connected, so there are no traps here, then the result is as follows. The limit is Excuberonian motion, but it is not so simple how to find this parameter gamma. Or the question may be the following one. You consider here a random walk, not only symmetric 1/2 up and 1/2 down. Increments are just random variables with random variables that are mean zero and have finite variance. And you have some perturbation here and some regular behavior here. And the question is, what is the limit? And again, usually the limit is Excuberonian motion if jumps from this irregular set are have a finite expectation. There are different ways how to prove the following convergence. Harrison and Shep, they just calculated finite dimensional distribution explicitly. Harrison and Shep, finite dimensional distribution plus compactness. But it's almost impossible to find a nice formula for finite dimensional distributions in this model. And this approach is almost impossible. However, Ngo and Penier recently used a similar approach and proved that the limit is Excuberonian motion and identified this parameter gamma. They didn't find explicitly formulas for finite dimensional distribution, but they got some nice estimates for finite dimensional distributions. Another approach is was done by Minlos and Zhizhina. They used semi-group approach. They calculated, they studied generators of, well, some generators for this random walk and proved that you have some semi-groups or some generators convergence for generator of Excuberonian motion. And if you have convergence of semi-groups, then it's very closely related to weak convergence of processes. However, there are a lot of difficulties in this direction because when you have a walk, you have a discrete, well, not semi-group, but some discrete structure, and it for Excuberonian motion, you have continuous structure, and it's not so easy to prove convergence of semi-group in terms of convergence of generators, because you have to care about domain. And generator here is 1/2 times second derivative, but domain is, or the, how to say, kernel of the domain is twice continuously finite twice continuously differentiable function that have some boundary condition at boundary conjugate condition at 0. And for random walks, well, for random walks, it is not so straightforward to see that generators converge to a generator of this Excuberonian motion. I have a few papers with Yuri Prihodko. And we use some probabilistic approach. Maybe it is close to Eta Excursion Theory. We studied behavior above this membrane, before this membrane, and we calculated probability that excursion is above or below and pass to a limit. And another approach is Martingale characterization. Characterization or Martingale problem. And we developed this technique with Alexander Igzanov. And I will use this approach for two-dimensional case, for multi-dimensional case that I will consider today. So I will tell you about Martingale problem a little bit later. Well, let me recall you multi-dimensional, or now I consider only two-dimensional case. So we consider two-dimensional case. We have some irregular jumps from this line, and assume that period is D. Period equals D. Now I will draw a picture when D equals 3. Okay, so let me color 0 point and 0.3 and 6 and -3 in red color. For example, 1, 4, -2, and so on by blue, and these points by green. And we have the following block. We have such blocks of three points: red, blue, green. Now I would like to consider some analog of excursions for two-dimensional random walk. Assume for simplicity that we start from y-axis. For example, assume that we start from this point, go to the right, here, and so on, and then you return to y-axis. So I will say that this is excursion. For example, you jump from this point here, and then go to the left here, here, here. So this is a second excursion, and so on and so forth. So these are excursions. Well, and let me denote.
I'm sorry. So excursion means that we have to return to the same color?
No. Oh, no. For example, yes, you may go here, and then you come here. So this is the second excursion. But you see, from blue point, you may have some transitions probabilities from blue point, and transition probability from green point are different. So jump to the right from blue point, from this blue point, and from this. So probability from this point go to the right equals probability from this point to the right. But from green point, this probability may be different. So that's why it is important. Do we start from blue point, or do we start now from green point and have another excursions? So probabilities here are 1/4 up, down, to the left and to the right, but probabilities from the first point are different. I need one definition. Assume that n is an integer number, and let sigma n be the last time before n when you visit this membrane. So this is infimum of k less than or equal to n, such that y k is 0. And let me introduce one more notation. X j plus or minus n equals absolute values of n times indicator of y sigma n equals j modulus d. And xn is positive if we write here plus, and is negative if xn is negative. So what does it mean? So let me color this excursion in blue color if we start from blue. Let me color excursion in green color, say here, if I start from green. So J is like label, is a color of excursion, blue excursion or green excursion. So if you start excursion from red, it will be red excursion. And plus and minus means the following. Plus means that you go to the right half space, and minus if you go to the left half space. So here x coordinate is positive. Here x coordinate is negative. So this excursion means that you consider x green negative of n. And I would like to say that, well, if j is blue, but at the moment n you have green excursion, then xj equals 0. Let me notice that x of n equals sum over j from 0 to d minus 1. So all colors xj plus of n minus xj minus of n. And yes. And I wish to say that only one number in this sum may be non-zero. So if color is wrong, or if you are in positive direction, so if you are in positive direction, then all these terms are zeros. So only one of these numbers may be non-zero.
So you must to have a right color and to be on the right side.
Yes, yes, exactly. We must have correct color and correct sign. And now, instead of studying this process x of t, I would like to consider the following process: xj plus of nt, xj minus of nt divided by square root of n divided by square root of n, where j's are from 0 to d minus 1. So this is 2D dimensional vector. So here there are all colors and all signs, pluses or minuses. And I would like to find a limit of this 2D dimensional stochastic process. So these are some labels. And now let's notice that only one coordinate in this process may be non-zero. And if you consider sum of all coordinates, if you consider sum j from 0 to d minus 1 x j plus of n plus x j minus of n, then this is a random walk on integer numbers, in natural numbers with 0, with reflection at 0, and transition probabilities are as follows. If you hit 0, then you go up with probability 1. And if you are here, if you are above 0, you go up with probability 1 over 2 divided by m. You go down with probability 1 over 2 over m. And you go to this direction with probability 1 minus 1 over m. Indeed, if your initial,
what is m here? I'm sorry.
M now m is dimension of a space. Dimension of a space. Now m is 2.
Okay, I see.
And now, excuse me, something goes wrong. And do you see my pictures or not?
No,
No.
you have to start your sharing again. Start to share your screen.
Let me try. Okay. Now m is 2, so here
Yes, we see now.
is 1/4, here is 1/2, and here is 1/4. Indeed, if you consider only horizontal coordinate, and if the horizontal coordinate is not 0, then you go to the right with probability 1/4, you go to the left with probability 1/4, and vertical coordinate is not changing with probability 1/4 plus 1/4, 1/2. So with probability 1/2. So so this is some random walk, such random walk. And it can be, well, seen that if you consider Donsker scaling for this random walk, and if you multiply it by square root of m, okay, times square root of m, then the weak limit is absolute value of a linear process. So here we have a weak convergence in a Skorokhod space. And square root of m is, well, m is just 1 over m is variance of a jump here. So if we multiply by square root of m, then variance of jumps above 0 are 1, and from 0 you have just reflection above. I will not prove this result, but it seems to me that this is some mathematical folklore. However, this result follows from our papers with Alexander Iksanov or Yuri Prihodko, and the proof is not difficult. Moreover, if you calculate if you consider this process in t over square root of n, and if you count number of visits to 0, and multiply this vector by square root of n, so this is number of visits to 0, then the result will be a pair, a Brownian motion, and a local time of symmetric local time of this Brownian motion at 0. Local time at 0. And well, we have convergence not only of one-dimensional distribution, but a convergence of processes. And now, assume that I find a limit of this vector. Then x of n is just a continuous functional of this process. We add these coordinates and we subtract other coordinates. Then if I show that the limit process is continuous, then description of the limit of x and t over square root of n will be a corollary of continuous mapping theorem. So my aim is to find the limit of this sequence. And the answer is the limit of this sequence is a Walsh-Brownian motion. And now I would like to give a definition to explain what is a Walsh-Brownian motion and give Martingale characterization of a Walsh-Brownian motion, and then explain how to prove convergence of this sequence to a Walsh-Brownian motion. I would like to make one remark about weak relative compactness. So this sequence is weak relative compact in Skorokhod space, and any limit point is a continuous process. To show weak relative compactness, we have to study modulus of continuity. And it can be seen that modulus of continuity of this sequence is can be bounded from above by modulus of continuity of this sequence of sequence x with tilde, maybe multiplied by 2. And if we know that this sequence weakly converges to a continuous process, then we have nice estimates for modulus of continuity for these. So we have nice estimates for modulus of continuities of this sequence. So any limit point is continuous process. Now let me give you a definition of a Walsh-Brownian motion and Martingale characterization of a Walsh-Brownian motion. Walsh-Brownian motion. Walsh-Brownian motion is an analog of a Excuberonian motion. Assume that you, let's consider space R2 and few rays. With vertex at 0. So the 1, 2, and okay, this is third. And Walsh-Brownian motion, the phase space is these 3 rays or m rays or some n rays with, so this is a phase space. And if you are here, you behave like a Brownian motion. If you are here, you behave like a Brownian motion on this line. If you are here, you behave like a Brownian motion on this line. And when you hit 0, then the next excursion will be like excursion of a Brownian motion on this ray or this ray or this ray. And you select rays with probabilities P1, P2, P3, and so on. So if 3 rays, then P1, P2, P3, where P1 and P2 and P3 are probabilities, and sum of Pj's is 1. So it's like first construction of a Excuberonian motion. It can be written transition probability densities.
But we have a process that on graph, not in R2.
Yes, yes, we have a process on graph.
On a star graph.
On a star graph, correct.
Yeah.
But it's easier to consider a process even not in a graph, not in R2, but in, assume that you have, say, M rays. Let's consider a process on 0 infinity to the power M. And if you are here, then, okay, x1 is distance from your process to 0, if you are on the first ray. x2 is a distance from the point on the second ray to 0, and so on, xm of t. And x1 is 0 if you are not on this ray. So only one of these coordinates may be non-zero, And if, say, xj of t is not 0, then your process is on the j's ray.
So we have a process in Rm, and the process
Yes.
lives only on coordinate.
Yes,
axis.
yes, you correct. You are on the Rn. So now assume that this is a picture in R3 and you have only 3 coordinate axes. So you live only on coordinate axis. So it's easier to consider this picture than a picture on graph or a picture in R2. And equivalent.
I do not understand what does mean the picture in R2. Just having the graph on R2.
Yes, just
realization of a graph as a subspace.
Realization. So it was initial approach of Walsh. So consider realization of graph in R2 and then study a process only on this graph. And graph is subset of R2.
Okay, I see. Thank you.
You have a description via this P1, P2, P3 selection of array, and the theorem is the following: a process xt. Yes, and what is the definition of a local time of a process at 0? The definition of a local time is as follows. You just take epsilon, ball radius of epsilon, calculate time that the process spent in this ball, and then divide this time by 2 epsilon, and then send epsilon to 0. And if this limit exists, you say that this is this limit is a local time at 0.
Does this approach brings this approach the same for different realizations in Rm or R2?
The same. The result is the same.
Okay, thank you.
Actually, and if you consider x1 of t plus xm of t, this process is just reflected Brownian motion. And the local time of Walsh Brownian motion at 0 just coincide with symmetric local time of reflected Brownian motion at 0.
Which dimensional Brownian motion?
Is of one-dimensional Brownian motion.
Mm-hmm.
Of one-dimensional Brownian motion. Result is as follows. Let xt, L of t, be a Walsh Brownian motion with a local time at 0. So a process XT-LT is a Walsh-Brownian motion with a local time if and only if the following conditions are satisfied. The first condition: only one coordinate of this process is non-zero. Xi of t times xj of t is 0 for all I and j. I is not j. The second, the process mi of t, which is xi of t minus pi times L of t are continuous martingales. Yeah, and this process should be continuous. Are martingales with respect to filtration generated by X. And this filtration should be, how to say, completed by sets of probability 0. The third assumption, L of t is non-decreasing process, and L of 0 is 0. And the first assumption that the process L of t may increase only when the process X visit 0. So integral of indicator X of t is not 0 dAt is 0 almost surely. So L of t does not increase when X is not in 0. And the fifth assumption is as follows, is the following. The process X does not spend positive time at 0. Almost surely. So this process, this multidimensional process spends 0 time at 0. Okay, this theorem follows from result of Barlow, Pittman, and York. Barlow, Pittman, and York, 1989.
Andrey, can I ask you one more about the relation between L and X? Because from the conditions, it is not clear where how they are related.
How are related X and
start,
what?
X and L. We start from arbitrary pair, or we build already L.
No, assume that X and L is a Walsh-Brownian motion and L of t is a local time. Then,
yes, then I understand, but I don't understand the backward.
And another implication is the following. Assume that X and L is a pair of processes such that then X is a Walsh-Brownian motion and L is its local time at 0.
I don't understand the last statement because at least if you have a processes which satisfy condition 1 to 5, and you just multiply your L at on some positive constant, you will have the same.
Thank you very much. And I forget to write, thanks a lot. I forgot to write square characteristic. Yes, and square characteristic is integral from 0 to t time spent of i's process on the positive line, not in 0. So the time spent on i's ray, on i's coordinate axis, plus this.
And then
if you multiply x by a constant,
yes.
then here you multiply.
Now we have the relationship.
Yes, and if you add all x's, then you will see that sum of x's.
Yes, and we can just use characterization of the local time for usual Brownian
for
motion.
Reflected, then you have Martingale problem for reflected Brownian motion.
Yeah, I see.
And now let me recall you. So this index, it is like a label. It's like a label. And now we have the following. Actually, let me recall you the definition of Excuberonian motion. Do you remember construction with probabilities? And you can consider, so it follows just from the definition that if you have a Walsh-Brownian motion, and if you consider the following process, sum of some coordinates with plus and subtract all other coordinates, A is some set of subindexes, then you get just Skew-Brownian motion. Skew-Brownian motion. So it follows from constructions when we toss a coin and select excursion with certain probabilities. So if we have some process that satisfies these conditions, and you add some coordinates and subtract other coordinates, then you have a Excuberonian motion. And let me recall you my random walk. I add some coordinates and I subtract other coordinates. Do you remember random walks with label scalar plus sign, plus or minus? So if I prove that this sequence x, j plus minus nt over square root of n, well, multiplied by square root of m, converges to a process that satisfies this, then there is nothing to prove. Then I apply continuous mapping theorem and this result. And that's all. And now here, let us discuss a few conditions, some conditions. For example, here only one coordinate is not 0. Then any limit point is such that the first assumption holds. Well, analog of L of t will be number of visits to 0. And I will prove convergence of these processes and number of visits to 0. And number of visits to 0 is not decreasing process, so its limit is non-decreasing process. Well, and I told you that number visits of zeros converges to a local time of a sum of these coordinates. So if you sum these coordinates, you get reflected Brownian motion. Actually, for this, you also get reflected Brownian motion. So it is not so difficult to prove that for any limit point, you also have this and this. because if you add coordinates, then you get reflected Brownian motion, and for reflected Brownian motion, you know this, that reflected Brownian motion spent 0 time at 0, and that a local time of reflected Brownian motion is not increasing when reflected Brownian motion is not in 0. You have to, so the most difficult problem is to write what is analog of these martingales. And let me just give you analog of martingales and analog of this. Consider this sequence. For example, I draw a blue excursion, and I consider only horizontal coordinate. When you are here, then x equals sum of independent identically distributed random variables with distribution 1 over 2m. You add 1 with probability 1 over 2m. So now it's 1/4. You add -1, and with probability 1/2, you add 0. For example, here you add 0, here you add 0 to vertical coordinates. If you consider green excursion, then you add nothing to blue excursion. So it's wrong color. So x, say j plus of n is sum of such random variables, say xi case, k from 0 to n minus 1, indicator that you have correct color and correct size at the moment k. Let me write correct color plus sign at the moment k. Plus, look, if you are here, then you add xi k, but the first jump may have different distribution. So the jump from 0 is different. Plus some, let me write, jumps from 0. If you make Donsko's scaling, so this sequence is a martingale difference. If you multiply by square root of m, then variance of xi k is just 1. And Donsko's scaling of this sequence will be a martingale of a continuous martingale with square characteristic integral of 1 to t, indicator that the limit process is positive, and the limit process with some label j and sign plus or minus. So intuitively, it's more or less clear. And properly normalized of this number of jumps from 0 will converge to a local time of times some proportion. So let me only write the probabilistic interpretation for this PIs. And I will not prove convergence of this part to a martingale and convergence of this part to Pi times the local time. So let me write. So it can be proved that xj. So this part is mj plus of or minus of n, and this let me denote lj plus or minus of n. So the limit of mj plus nt over square root of n will be pi times mj plus of t, where this process is a local continuous martingale whose characteristic is integral from 0 to t, indicator that the limit the limit point for this sequence is positive. And now, what are Pi? Let us consider sequential. Let us consider returns to this membrane, and I color these points in red, green, blue. Red, green, blue. So red, only in these blocks. So let the instant of first return is tau 1, instant of the second return is tau 2, the third return is tau 3. And let's consider a sequence y of tau 1 modulus 3. Now 3 is period. This will be, say, the first element, y hat 1. Y hat 2 is y at the moment tau 2, at the second return, modulus 3, and so on and so forth. So I just see colors. So red, then again red, for example, again red, then blue again, and then green, and so on and so forth. It's not difficult to show that this is a Markov chain, that this is a Markov chain on red, green, and blue. And let's consider the following sequence y tau 1 and x at the instant tau 1 plus 1, and the same here. So where we are and the sign, we go up or we go to the right or we go to the left. So this means color, and this means sign of excursion, plus or minus. Again, this is also Markov chain. it can be seen that this Markov chain, that all states are connected, and the period of this Markov chain is 1, and we have stationary distribution. And these probabilities here.
Excuse me,
Yes.
why we know that all states are connected?
Because
Do you suppose something on
no,
this
because
transition probability?
if you from membrane you go to the left and to the right, and
then I have just simple
yes,
random
you have simple random walk, and
yes,
probability 1 you can hit
any point.
Yeah,
Okay,
any point.
yes.
And period is 1 because you.
Yes, surely.
It's not, well, it's easy to see. So these probabilities are just stationary probability of this random walk. And we have to write here color and the corresponding sign, and that's all. So this is the answer for the first coordinate. So the first coordinate is Excuberonian motion. And what is the second coordinate?
But maybe this probability can be calculated if you know transition probabilities from this vertical axis.
Well, I think that they solve some linear equations, but I'm not sure that the answer is nice.
Yes, but this is just excursion of.
Actually, I know that, well, it is not difficult to show that Pj plus Pj, well, I don't know, sorry. No, I don't know. Well, if you don't have vertical drift, then you have uniform distribution.
Yes, exactly.
But if you have vertical drift, then there is not some nice formula. You have to study some linear equations, or maybe linear matrix equations.
I see, but actually it is a little bit strange because of uniformity of the distribution.
Distribution.
Why you don't think that if you have vertical drift, the distribution will not be uniform?
Okay, it is very easy. Okay, we calculated it explicitly. We have some counterexamples.
Okay, it will be interesting to see.
Even in more complicated situation, but the reasoning are following. Yes, okay. Let me make a picture. Assume that jumps are like this. From this point, you jump here or there. From this point, you jump here or there. And from this point, you jump here or there. So you are closer after you visit membrane.
Yeah.
You are closer to red point. So with higher probability, you will start in red point than in green or blue.
Yes.
So there will be more excursions that start on red, more excursions that start on red excursion.
And Okay, and but
So
the
if you start from
distribution,
this point, it's
yes.
more likely to hit this point than to hit this or this.
Why? Actually, this is my question. What we know about the distribution of the end of excursion? Yeah.
Yeah, I don't know the answer, how to find this distribution explicitly.
But because okay.
But it is not uniform.
Mhm. Okay, maybe, but it will be interesting to understand what happened exactly here.
Well, and for so this coordinate is Excuberonian motion, and vertical coordinate is as follows. So when you here, then you jump up or down or stay as where you are, and you have some additional drift when you start from membrane. And you know approximately the number of visits to this membrane, and you know approximately proportion of colors, red, green, or blue, and you know that number of visits to different colors are proportional to the local time of horizontal coordinate. So the answer is local. So the answer will be local time times local time of horizontal coordinate times some correction term. Because when what is additional drift? Additional drift is the number sum of some random variables from here. Number of visits, and you know that if you know a color, the correct color, then these random variables are independent and identical distributed, and distribution just depends on the color. So it's like a law of large numbers. So if you divide by L of n, then you'll get expectation of this jump times this proportion. So these are arguments. So this is not rigorous proof. So it's like to write more correct, it's like the following. Times sum color equals j, and sign for different signs, and times eta k and j, where and plus or minus, where k is an instant of time, j is the corresponding color, and plus or minus is a corresponding sign. So it is like sum of function of a random walk of a Markov chain and some independent identical distributed random variable. So it's like sum of some function of some random walk and some random variable which is conditionally independent of this. So, and there are results on laws of large numbers of such functional. So it's well known.
Okay.
So these are arguments for explaining why additional term for vertical coordinate is a local time of a horizontal coordinate times some constant. So stochastic differential equation for the limit process will be like this. dxt is dwxt plus some parameter gamma local time of x at 0, Ascubronian motion, and for another coordinate we have another independent Brownian motion plus some constant times a local time of x, not of y, but of x at 0. Okay, so that's all for today. Thank you for your attention.
Okay, thank you very much for interesting talk. And let me ask you this gamma, we know it is related to some probabilities and its value cannot be greater than 1, its absolute value.
Yes.
What about C? I think that
C may be
on C you
arbitrary.
haven't such
Yeah.
conditions. Yeah?
C may be arbitrary, yes,
Mhm.
and it's not difficult to find examples for arbitrary C.
Mhm. Okay. Yeah. Mhm. And you mentioned the different dimensions, but maybe in different dimension you can also consider more complicated membranes.
So in multi-dimensional case, we can study, okay, so we have x coordinate dimension y, and we have y coordinate dimension m minus 1. So it's like in three-dimensional case, it's like plane that's separated two half spaces.
Mhm.
And we know how to study membrane that have some periodicity in each direction.
You see, it was actually my question because it's very similar to some averaging principle for such singular equation. Yeah.
Yes, it's like some averaging principle. Yes.
Mhm.
So you see, for horizontal coordinate, yes, we consider only labels. So only labels, and we start. The proof will be the same. We study the color and the sign of excursion, and then we prove convergence for this coordinate, and then behavior of all other coordinates is some martingale plus some sum that depends on number of visits to different colors, and that's all. And then you have some averaging here, and you get some vector drift in this y dimension. We also have some generalization when membrane is not periodic, but possess some ergodic structure.
Yeah.
Ergodic structure, but for example, probabilities to go to the right from membrane or to the left are independent, identical, distributed random variables. So you have some random environment.
You see, it is interesting two circumstances here. The one is that for periodic drift or even for periodic diffusion coefficients, Oleynik, Kozlov, and Zhikov, they studied purely deterministic problem of averaging principle for parabolic equations, but they do exactly the same. They considered firstly the dynamic system, ergodic dynamic system, which describe the structure of which leads to the averaging, and then it is closely related to random media, random walk with such a singular random media, I think. So maybe works of Mogulski also can be interesting for you, because he considered averaging principle relatively for diffusion process, relatively to this ergodic properties of random media.
Thank you very much for these references.
And I think you mentioned in the beginning of the talk, maybe Jana knows something about this and can correct me, that
No, I don't think so.
the approach based on the semi-groups and convergence of operator can be modified for averaging. Actually, Kozlov, Zhikov, and Oleynik did this. And they use interesting notion of convergence for functions. So if you have a look, maybe it will be interesting and useful.
Okay, thanks. Well, we have some other also some other generalization when membrane is two-sided. For example, you may have, for example, here the wall. So if you come here, then you reflect. But here it may be like also the wall, or you may have just door to this direction. So when you come here, for example, you push 100% to the left. You may have a wall here and a wall here. So imagine that if you hit here, then you go to the right. But if you hit here, you go to the left. It is not a Markov chain. So this sequence is not a Markov chain, but it can be considered as a Markov chain if you enlarge state space and say, okay, this, when you come from the left, it is 0 minus, and if you come from the right, it is like 0 plus. 0 plus, and the result is the same. The limit is, if you have periodic structure here and there, then the limit is Excuberonian motion. And it's interesting. If you have periodic structure here and periodic structure here,
but different.
No, different. But if you shift a little bit, then parameter of permeability may be different.
So if you do averaging of singular coefficients, this singularity can change.
Yes, yeah. For example, you have here some green, red, green, blue, and here you have, say, red, also period 2, red, yellow, red, yellow. And if you see, if you change red for yellow and yellow from red, then the result may be different. Maybe different, and we calculated just these numbers, some explicit examples, and we get different parameters gamma.
Interesting.
So imagine that you have like two half planes and you want to glue them together. So a parameter of permeability depends on the way of gluing. If you shift a little bit, you may get another parameter of permeability.
I see. Okay, maybe some other questions or comments, please. If there are no questions, then we have to thank our speaker again. And this is our last session before summer vacations. So I wish everybody to have a good summer, have a rest, to write a lot of good papers, and prepare the talk for new semester. And don't forget that in the middle of August, we collect the titles of the talk for the new semester. Hope to see everybody back at the September. I wish you good summer. Bye.
Thank you. Goodbye.
Thank you. Bye.